Department of Geology and Department of Biology at the University of Washington in Seattle. Well, the Earth has certainly gone through a lot of hot times and cold times, back and forth and back. And what I do is I study deep time by looking at CO2 levels and relative temperatures. And we are coming out of a cold time and moving into a hot time. However, for this particular time in history, we should be moving back in a cold time. If we take the entire ice ages, the last 2.5 million years, we've been in a 10,000 year calm of warmth. And it's time to go cold again. And yet, doesn't seem to be in our cards because of all the carbon dioxide we have put into the system. And in fact, we are now at levels that the world has not seen for the last 40 million years. And we will soon be at carbon dioxide levels that were 100 million years ago when we had a true hothouse world. So the game has been changed. Our Antarctic work is to look at the nature of global temperatures at the end of the Cretaceous period. The Cretaceous ended 65 million years ago. The putative end, and I do believe this, is that a large asteroid hit us in the Yucatan Peninsula, causing a mass extinction. But we're trying to see what happened in, say, the 10 million years prior to that, because we know at that time there was a gigantic volcanic event in India. These are big flood basalts, they're called. It's not a single point source volcano, but imagine enormous areas of the Earth, creeping lava coming out of cracks and flowing slowly all around, scaring dinosaurs to death, probably running in front of the stuff. Probably killed a few dinosaurs, but what it did do is it vent an enormous quantity of volcanic carbon dioxide and other gases into the atmosphere. Now we wanted to know, was there any precursor to the impact? Was the impact just a coup de grace coming on an already affected world? And it does seem to be that. And the best place to look at this, the best place to understand anything about global warming isn't at the tropics. That's where temperatures change the least, but it's at the poles where you have the greatest absolute change. And so we found a 10 degrees centigrade change from colder to warmer in the last 2 or 3 million years prior to the impact itself. The place really did warm up and fast from a lot of CO2 into the atmosphere. Now there's obviously parallels to what's going on in the world today. Yeah, we're trying to understand past temperatures, and you can do this in a couple of direct and indirect ways. But the most direct way is to take the shells, if it's unaltered, the original shell of some of the mollusks that lived at that time. The ones we look at are relatives to the chambered nautilus called ammonites, beautiful pearly shell, and just run an isotope check on it. You can do this very simply by crunching it up, turning it into a powder and heating that. You get oxygen being driven off. You compare the isotopes. It's been known for 50 years that a comparison of the oxygen isotope 18, which is heavier, to the far more normal oxygen 16 is a direct way of measuring ancient temperatures. So all we try to do is understand, gee, what happened to ocean temperatures across this 2 or 3 million year interval? So we collect the specimens, we take them back to our labs in America, we run them through the machines and came up with a temperature curve. So we do have a direct measurement now of, say, the last 5 million years of the Cretaceous and its temperatures in the Arctic and Antarctic. And sure enough, those are the places that should warm up the most if you had a global warming scenario. And in fact, that's exactly what happened. Well, the differences are just simply what is causing it. I mean, in the past it was volcanoes, and today it's Volvos, or any other car you want to say. But in reality, it's not even the cars. And see, this is a misnomer that I see. We think of all those cars and all the exhaust from them, and surely that is a problem. But it's the power plants that make the steel that make the cars. That's the problem. Power plants are the big problem on this planet. And that's why we really have to think seriously about China, with its billion or more people, of which 1 in 100 has a personal car. America has 300 million people and over 300 million cars. Now what happens if the world has to build 1 billion cars just for the Chinese? That's a lot of carbon dioxide still to go into the atmosphere, a lot of power plants, and the power plants in China are almost invariably fueled by coal. And coal is the single worst polluter that humans could use. Well, we certainly know that we were hit 65 million years ago by a very large rock from space. Hollywood knows this with the two blockbusters, Armageddon and Deep Impact, so it must be true. It was really interesting. In '95, Spielberg sent his minions to a conference a number of us were attending about this particular hit. And indeed, there is great danger out there. We are surrounded by asteroids. Some become Earth-crossing. Jupiter has a way of perturbing comets and sending them from stable orbits to Earth-crossing orbits. We will get hit again. How big the hit will be is only a matter of time until we get something that's the same size that killed off the dinosaurs. Showed humanity last long enough, that is. But that size hit looks like only once in 100 million years or more. We haven't had a hit that size for the last 500 million years. So it does look like it's a rare event to have something that big, a 10-kilometer asteroid, hit us. Well, no, it's just the whole sense of when is it going to happen again. And it appears that most of the big mass extinctions have been caused by these nasty volcanic events. The last one didn't cause a mass extinction. It was in the Tertiary period. This was in my own home state, Washington State, the Columbia River basalts. Out came all this basalt, this liquid lava, and a lot of carbon dioxide came out too, but not enough to cause the Earth to go into a really nasty mass extinction. The mass extinction is caused by the basalts, again, or simply by heating the world. Now, when you heat the world, you heat the poles more than you do the equatorial region. When that happens, you start losing circulation. The only reason you have wind now is you have a hot spot and a cold spot, and they're trying to equilibrate. Well, in ocean currents, same thing. You have a cold Arctic, a cold Antarctic, and then you warm them up. The ocean circulation systems dampen down. There's much less heat difference. So when we heated the poles to the point that there was no longer or only very sluggish ocean circulation, the oceans go anoxic. They lose their oxygen. They only keep oxygenated now because of this vigorous mixing. Well, even when you have oxygen in the atmosphere in contact with the surface, once you slow down any circulation, that whole basin can lose its oxygen. The Black Sea is the same case. It sits under a 21% oxygen atmosphere, and yet the Black Sea, except for the top several meters, is anoxic. It's black because it's producing a lot of sulfur-producing bacteria, and there's very nasty gases that are produced. We now think the big mass extinctions were caused by global anoxia. The oceans themselves so sluggish that the hydrogen sulfide bacteria are produced in huge areas of the ocean bottom, bubbles up to the surface, and starts killing things, rotten egg killing. It would be extremely nasty. Hydrogen sulfide poisoning is a horrible death. 200 hydrogen sulfide molecules among 1 million air molecules is enough to kill a human. I mean, just breathing in 200 of those little things, amid all the million you've got of oxygen, and boom, you're down, horribly down. So this is a really nasty poison, and it was certainly present in past oceans during these short-term global warming events. That's why it's really spooky what we're doing now. Our best hope is, we just saw our best hope. It was the global recession we just saw. Because economic activity dropped, we had less carbon dioxide going into the atmosphere through emissions, and yet that recession has caused what? Untold misery for a whole lot of people. 10% unemployment in the United States is going to be endemic for a long time, it looks like. That's misery. But the misery that will be caused, the economic chaos that will be caused if we melt ice sheets in any significant matter, is something that I have never yet seen outlined, and it scares the heck out of me. Let's think about just a 3-foot sea level rise. If we never put another CO2 molecule into the atmosphere, that's still going to rise 3 feet. If it rises 3 feet, what happens to all the ports and all the docks on the whole planet where ships come in and offload? Now, that high tide is going to take that ship 3 feet higher than it ever did before. All of a sudden, that dock isn't quite in the right spot. When you have a lot of other docks all over the planet, you start talking about billions of dollars. In fact, CNN came out with a report in the last month that simply a 3-foot sea level rise will cost trillions of dollars around the planet on simply fixing the wharfs. Now, what else does a 3-foot sea level rise do? You can say goodbye to JFK Airport. You can say goodbye to LaGuardia. You can say goodbye to Hawaii, San Francisco, Auckland. Where else have I been? All over the planet, we put airports right on sea level. Airports cost billions of dollars. So you've got trillions of dollars in airport rebuilding. 3-foot sea level takes out a significant portion of the world's crops. A great amount of foodstuff is produced at sea level or within 3 feet of it. The San Joaquin Valley, the greatest foodstuff producer in America for vegetables, a 3-foot sea level rise will cost huge amounts of salt going into that system, which is already vulnerable to it anyway. The economic impact of a 3-foot sea level rise is incalculable, except the 3 foot is just the start. Well, I think we're going to survive. I don't think climate change can make us go extinct unless we produce so much CO2 in the atmosphere that once again we shut down the conveyor belt currents. These are the largest scale currents in the ocean. They are from the surface to the bottom currents, not just sideways currents. And so they are the current conveyor that takes oxygen from the top and takes it to the bottom. If we lose that, then the bottoms of the oceans go anoxic and you start down this road towards what we call greenhouse extinctions, which is the hydrogen sulfide events. It would take tens of thousands of years to get to that. But we as a species have only been around for a couple 100,000 years. The average mammal lasts 5 million years. Are we anything less than average? So we should have a few million years left, even if we're average. We're not average. We could be living fossils in the last 500 million years. There's nothing genetically within us that says we have to go extinct. Unfortunately, I have these genes in me that are going to kill me, and all your listeners too. But as a species, we don't have those genes. Species don't age out of existence. Species are killed off, lose competition. They go extinct because they're driven to extinction. It's not inherent. It's not within them. So we keep track of Mother Earth and do some good engineering, and we're not going to go extinct. But extinction and misery are two different things. Not going extinct doesn't mean you're not going to be miserable. And by misery, I mean wholesale, enormous human mortality. I think all life is suicidal. I thought up tongue-in-cheek sort of the Medea hypothesis. Medea, Jason's wife, was probably the worst mother in Greek history. She murdered her children because of Jason's infidelities. Jason was probably not very good at anything, apparently, except making women fall in love with him. He was good at that. He got the fleece back. He wasn't much of a captain. He wasn't a fighter. Whatever. The Gaia hypothesis suggests that Mother Gaia, who's the Greek mother, will sustain life, keeps life going. The kernel of that hypothesis is that life makes the world better for itself, that through regulation and a number of systems, life is increasing habitability. It's kind of like I'm in a hotel right now, and in my hotel, before I leave, I paint the walls and I put in a better stereo system or something. I'm making the place better for my having been there. Well, that's really what the Gaia hypothesis suggests, whereas if you really look at the history of life on this planet, you see a lot of biologically produced catastrophes. And that's really what Medea is suggesting, that life is, it's the global warming that starts the process, but the killing comes from the hydrogen sulfide. And where does that come from? That comes from microbes, from life itself. So life is the bullet if the gun itself is the volcano. Intelligence is the only way out. I would suspect that all life is inherently Median, and the reason being, if we think of the definition of life, it metabolizes, it reproduces, and it evolves through Darwinian selection. Now, that's the NASA definition. Darwinian selection means that you produce more offspring than can possibly live, so competition is built into life. You compete not only with other species, but with yourself. The competition in this entire system leads to one species trying to take over the whole planet. I mean, it's built into every species wishes it could be dominant. It's just built into the system. It's part of the basic fabric of life. The only out on this, because the ultimate end result of one species taking over is eventual life, the death of all life on the planet itself. The only out is intelligence. Only an intelligent creature can realize how this system works and begin the engineering that can keep planetary life-giving systems like carbon cycles, nitrogen cycles, all of those going. Unless intelligence is there, it's going to completely break down, and that's the end of life on this planet. Well, when we thought up the rare earth hypothesis, it was simply taking a look at what happened on this planet that allowed us to have multicellularity. Part of it was that we had conditions allowing habitability for billions of years. It took a long time to get to something as simple as a two-celled creature. A long time. How do you get a long time? You do it because systems of temperature, systems of oxygen, systems of all the gases and the carbon movement remains stable. If you get too hot, too cold, and only a little bit too hot and a little bit too cold on a planetary sense, you kiss it all goodbye. So what is it about the Earth that allowed those things to continue for such long periods of time? The most important is plate tectonics. This is the movement of the surface of the Earth over the top of a mobile, softer rock substrate beneath it. So the continents skate around like bumper cars. But part of that process is a continental and an ocean recycling. And that recycling system is inherently, it's the absolute necessity to keeping long-term temperature constancy. We have this feedback system, a thermostat system. What makes the Earth warmer is carbon dioxide. What makes the Earth cooler, interestingly enough, is the removal of that carbon dioxide. Volcanoes put it in the air, but weathering removes it. If you take a granite or any rock that had volcanic material in it and let it chemically weather, one of the byproducts takes CO2 out of the atmosphere. The warmer it gets, the faster that process works. And so the warmer it gets, the faster the breakdown removes CO2. If you get down to an area or a level at which you no longer chemically weather, the volcanoes refill you up. Now that bang-bang feedback system has been in service here for over 3.5 billion years or more. That has kept us at a stable temperature. How often does a planet have plate tectonics? By looking at the nature of the rock, we barely have it. If you want to think about the end of the world is going to happen when the coefficient of sliding rock, when the friction coefficients overexceed the type of rock we have, we no longer have these subduction zones. The end of the world is also going to be when our core, we have this liquid molten core, it's going to freeze because the Earth is slowly dying and cooling. When that freezes, we lose our magnetic field. And so we also have consequences for plate tectonics. Losing the magnetic field, losing plate tectonics will definitely be the end of life on this planet. And so those two things are geologically produced. How often do you find both of them in the same planet? Theoretical studies say not very often. What if we didn't have a good Jupiter but had a bad Jupiter? Well, then you can really kiss it all goodbye. A highly elliptical Jupiter ends up either causing the inner planets, the rocky Earth-like planets, to be ejected into space or pushed into the star itself. I mean, obviously that's a death sentence either way. You've got to have a good Jupiter. The other complete unknown is how much ocean do you get from asteroids coming in? The oceans we have on this planet are a byproduct not just of water on the Earth when it was formed, but lots of comets that came in early in Earth history. Now, if we have too much water, let's say we had an additional ocean to the point that we don't have land sticking out of the water, well, then this feedback system, the temperature system doesn't work. You've got to have, what's really scary is that you might have to have ocean-land mixes of this 2/3, 1/3, or even half-half to make the whole system work. You have to have rock out, you have to have oceans to have water, but how much of each? And the modeling is just starting, and it's a little spooky. And it really does look like there's not going to be a lot of Earth-like planets. Let's take the last part, our moon. Here's the scary deal. So in Caltech, new calculations, let's say we have no moon. And obviously looking at this solar system, Venus doesn't have a moon like ours, Mars doesn't, Mercury doesn't. We're the only one that has an Earth-like planet with a moon that's an appreciable size of the planet itself. If that moon is not here, our day is 4 hours long. 2 hours of daylight, 2 hours of dark, 2 hours of daylight. Our spin rate increases so much. The moon is a brake on our spin. What happens to climate when you have a spinning Earth that has a 4-hour day instead of a 24-hour day? The entire climate system, radically different. Would it sustain life as it does now? Well, the models are just kicking in, but this one itself might actually have been something hugely important in allowing there to be as much complex life as there is now. Well, the Kepler missions, the satellites that are going to go out there and tell us how many Earth-like planets there are by blotting out images of the stars that are near so we can actually see disks. What's interesting now is we're an Earth-like planet. It looks like Earth is on the small end of what we now call Earth-like planets. We're seeing far more what we call super-Earths, which are about 2 times Earth, but they have a lot more gravity. There's going to be no way you would have complex life of our shapes in much higher gravity. You're certainly not going to have things flying around as we have. You would probably have different shapes of fish. You could get complex life, but it would certainly not look like the stuff we have now. It's just from the physics, the differences in water and air. I bet that's near zero. How could there be, with the numbers out there, how could there not be lots of them out there? But what is the possibility that there are so few that the distances involved make it so not even SETI couldn't find anybody else? I mean, SETI, we already know from the SETI work to date that there's nobody near us that's blasting out the sort of messages that the movie Contact is suggesting. I mean, that's not happening. And SETI itself agrees that, gee, if we don't find anybody in the next 30, 40 years, there's could be pretty good chance there's nobody close enough to us that we would ever be able to either talk to them, let alone get out there and see them. I suspect the chances are that we will not, at least in the next few centuries. Perhaps our technology will get to the point that we can pinpoint not just the immediate area, which is really all that we're good for now, and spotlight the entire galaxy. Or perhaps we get good enough that we can really start looking at other galaxies. I think then we'll start picking up evidence that there's other life out there. But if you're talking about places hundreds of thousands of light years away, there's no conversation you ever want to have waiting 100,000 years to get your response. And then it comes back to you and says, message garbled, please repeat. Well, it could be an aspect of communication, but it also could be just another indication that Medea is correct. The life gets going on a planet and then kills itself off through colossal blunders. A friend of mine said, well, I shouldn't call it the Medea hypothesis, but evolution is more like Mr. Bean. Mr. Bean blundering into one situation after another. You know, let's make oxygen. That'll be cool. And then poisoning almost every bit of life around it. Or, hey, let's make photosynthesis. And then reducing carbon dioxide so much that we go into a snowball Earth. Or, hey, let's make forests. And then reducing CO2 even further and producing a gigantic, almost global ice age in the Carboniferous. So, yeah, let's do this, says Mr. Bean. Oh, science is certainly affected by how scientists perceive they should be. And we're all human, human nature being what it is. It's really a shame that science as we know it now discourages scientists talking to people other than scientists. Carl Sagan knew much about this. We invented a word, Saganized, or Saganization, in which your fellow scientists frown on you for attempting to talk to the masses. The way it comes down is just sort of a prim downturning of the mouth. But the reaction is, why have you wasted your time? That's time that could have gone into doing your science, and you've taken it away and done something else. Well, I mean, you've not come to your full potential as a scientist. I personally am pretty upset about this in the sense that I think the reason that we have only half of Americans believing in evolution, the reason that we have so many Americans thinking that there's a political motive in global warming, is that the science communication coming out of the professional scientists, most of whom university professors, is abysmal. And here's an example. When you come up for a job interview, you have been vetted from 100 candidates. And the way that we cut down is looking at their scientific output. If this is a postdoc or some other brand new PhD, we're looking entirely at research productivity. If research productivity is marred by, there's an outreach component to this, that sets that person in deficit compared to that other person who got that one more scientific article. When we come up for promotion, we never look and say, hey, 2 scientific Americans. No, we saw, wow, 3 papers in science. Okay, that's what goes. You don't get promoted for the side stuff. When I write books, I've done 16 now, they don't go into my promotion packets. These are this sort of ugly little aside, the detritus that this person has been doing as a hobby, but it's not part of the professional me. It has nothing to do with me as my professorship position. That outreach stuff, that's somebody else. I should give it an entirely different name. And that's the way it is across all the first-rate science places. A lot of people do outreach, but not enough. We need to make that any PhD thesis, 1 chapter is outreach for the public, the other 3 or 4 are for the scientists, and that this has to become institutionalized, and you can't do it from one person. It's got to be an entire recognition. That's not happening. Well, if you look at PBS shows and look at the audience of the PBS science shows, they all have the hair color I do, gray. It's an aging, graying audience. The way we have to work now, and I fully believe this, is that we scientists have to stop writing the books we write or being on the TV or even being on programs like this and start writing video games. I've got a 12-year-old son. The only way to get to him is a video game. That's what he wants to do all the time. Video games are the way to get into his and all his friends' brain. Make happy, really cool first-person shooters that at the same time get across good science. That's the way to do it. I mean, I really have come to the conclusion that writing these books does virtually nothing. You've got to get to people who don't get it otherwise. Video games, to me, seems the logical way. Well, there was the old stereotype that women did more poorly in mathematics, and that has held for a long time. But to be honest, I don't believe, certainly in my career, I've seen the women in science problem diminish enormously. We have more women graduate students in my two departments than men. It's been that way for years now. So whether that's translating to the job market, are we hiring as many women scientists as men scientists? Well, there's still a function of there may be more men scientists in particular areas, but again, that's diminishing. So I'm hopeful that that particular aspect has changed. Seems to be. Well, there's a lot of misconceptions out there, dangerous misconceptions. The one I'm closest to is this Gaia hypothesis. The misconception is if we can only go back to nature, somehow the sense that if we can get rid of all the civilized trappings, that the world will heal itself. I think everybody has a sense that we have dented the world. We have certainly put our footprint upon it, and it may not be in the best particular way. But on the other hand, do you want to see the child misery, the childhood diseases? Do you want to see one out of every two babies die of early childhood death? And that's the way it used to be before we began the technology in medicine, technology in transportation and all things. Do we want to go back to that? I personally don't. And if we don't want to go back to that, then we're going to have to recognize that we're going to have a heavy footprint on this planet. The reality of the situation is that the world and everybody in the world wants to raise their standard of living. That in Africa, where I've spent a great deal of time, in Asia, there is this longing. There's cell phones everywhere now. You cannot stop the spread of the understanding of what other cultures have. Everybody wants it. And with this universal communication ability, you may have a cell phone, but you don't have a car. Well, you want that car. You can see the ads. You've got it all. You want that stuff. We're going to have to figure out how to raise standard of living in a gentle energy fashion, or as gently as we can, in terms of what's going to happen to the atmosphere. And this is where I personally think there's no stopping the rising sea level, that it's going to happen, that we're going to have to deal with it, that we're going to be moving cities, and that the next 2,000 to 3,000 years of human civilization shall be the movement of humans to higher ground. That will be the major motive. We're not going to conquer the solar system. We're not going to have the resources to do it. We're going to be way too preoccupied with changing the positions of our cities. My heroes were actually the great dinosaur hunters of the American Museum, Roy Chapman Andrews, Granger, and those guys. Sagan is certainly a hero. I have a lot of heroes within my own disciplines that are probably too arcane, but Stephen Jay Gould was perhaps my greatest hero. I knew him very well. I knew him well enough that I got in trouble a lot with him. He sort of viewed me as this cantankerous younger brother. He once told me, "Peter, you'll never be great, but you're pretty good." Now that's quite a slap in the face, right? We all want to be great. But it was from Steve saying, I'm great and you're not as great as me, but I like the fact that you're doing good work. And it was that sort of relationship. Okay. But I miss him. I miss his voice. He was the greatest single public speaker I've ever heard. He was also the smartest man I've ever known. I've known quite a few intelligent people, but his processing speed was beyond belief. And it's a great voice lost. The greatest single threat to us, again, is this rapid global warming, in the sense that I am really kept up at night worrying about the slowing of the circulation systems of the oceans, and kept up at night worrying a great deal about sea level rise. I have a book about to come out called Our Rising Sea, or Our Flooded World. They haven't finished it yet. We're doing a TV show about it. We'll start filming in March. But even 2 meters But after being in Antarctica, look, we melt Antarctica, we've got 240 feet of sea level rise. So where I'm sitting here in Manhattan is about 100 feet underwater. There's just going to be a whole change in geography of this planet due to industrialized humans. I think there's no stopping it.